Okay, welcome everybody. We're going to get started. For those of you who are new to Taste of Science, we're part of a national nonprofit science outreach organization for adults. Usually we'd be holding a big in-person science festival in cities across the US, inviting you to meet your friendly neighborhood scientists in your favorite spaces. But these days we only have the space in our homes and online, so we've gone digital. We have several virtual events planned throughout the next 2 weeks. Be sure to check them out at our website, which is tasteofscience.org. This particular event is being put on by our New York City chapter. And my name is Cynthia Gunderson, and I'm the city coordinator for the New York City chapter. So as you know, tonight's event is all about missions to Mars. So before I introduce our first speaker, I wanted to explain a little game that we're going to play during tonight's event. So it's bingo. So as I'm sure you all know, the point of bingo is to get 5 in a row in any direction. Your boards will contain words that our speakers may or may not say during their talks. And each time you hear a word, you can mark that square. And as I said, if you get 5 in a row in any direction, you win. So to create a board, you can click on the link to the Google Sheet that I pasted in the chat. All of these instructions should be in the chat. To make a unique board, you'll have to make a copy of the sheet. So to do that, you go to the File menu and select Make a Copy. You can name it anything you want. If you don't see a 5x5 board in your copy, just wait another minute. It takes a second to load and it'll look all wonky in the meantime. But it should work in about a minute. If it doesn't seem to be working, you can click refresh on your browser and that should solve the problem. And then when you hear a word during one of the talks, you can mark the square any way you want. You can highlight it or do strike through or bold it or change the colors, whatever you want to do. And if you get 5 in a row in any direction, you win. So you can, first of all, you can announce that you've won in the chat. And you can also take a screenshot of your board, or you can download the file by going to the File menu and download. And then you can email it to New York, spelled out, at tasteofscience.org, along with your mailing address, and we'll mail you an actual physical prize. Just to note that once you've started playing, don't refresh your Google Sheet or it'll refresh or reset your entire board. So don't do that. Okay, and if you have any questions about bingo, you can put them in the chat. One of us will try to help you. All right, so I want to introduce our first speaker tonight, which is our first speaker is Bruce Jakowski. Dr. Jakowski is a professor in the Laboratory for Atmospheric and Space Physics and the Department of Geological Sciences at the University of Colorado in Boulder, and he's the Associate Director of Science at the Laboratory for Atmospheric and Space Physics, LASP. He received his PhD in planetary science and geophysics from Caltech, and his research interests are in the geology of planetary surfaces, the evolution of the Martian atmosphere and climate, the potential for life on Mars and elsewhere, and philosophical and societal issues in astrobiology. He's the principal investigator, the PI, of the Mars Atmosphere and Volatile Evolution, or MAVEN, mission to Mars that has been orbiting Mars since fall of 2014. So without further ado, Bruce, the screen is yours.
Thank you, Britta. It's a real pleasure to be here and to be able to talk about my favorite planet and to help out with this game of Mars Bingo. I love that idea, and I will tell you, I'm very open to bribes if you tell me the words you want me to say. However, absent that, I'll be talking about what's going on in exploring Mars today. You should be seeing my cover chart full screen, is that right? Britta, please nod yes if you see it.
Yeah.
Thank you. I'm always a little skeptical. Mars is a really exciting place to be exploring right now. There's a lot going on. We have something, the world, the Earth has something like 8 orbiters actively operating at Mars and 3 4 spacecraft as of today operating on the surface. And I'd like to talk a little bit about why we're doing this and what's exciting. And I'm going to start with this idea that Mars is very much in the public eye today. Wherever you turn, you see something about Mars, from music groups seen in the upper left, the movie The Martian. If you're a Tesla fan or a SpaceX fan, you'll recognize the Starship launch in the lower left. And that thing in the lower right, if you know what it is, I don't have to tell you. And if you don't, there's no way I can explain it to you. But everywhere you go, it seems like Mars is in the public eye. It's very visible. It's an exciting place to be looking at. Let's start by comparing Earth and Mars. Mars is about half the size, half the diameter of the Earth. It's about 1.5 times as far away from the sun as the Earth is, so it's colder. The atmosphere is much thinner. You might ask, with such a thin atmosphere and temperatures well below freezing, why are we interested in Mars? And I'll give you an advance notice right now that the issue is the potential for life to be on Mars. And that's what I want to talk about. But I'm going to start by talking about some of the spacecraft that got there this year. We've sent an armada to Mars just this year. These pictures show the landing of the Perseverance rover. And I have to say, this is one of the most exciting sets of images I've ever seen, where they actually put cameras on it so that we could watch the landing. The parachute up in the top left, the sky crane that lowered the rover down to the surface in the upper right, and the rover itself in the lower right. That picture in the lower left is just the heat shield falling away to the surface. The landing was absolutely flawless just a couple of months ago, and the rover has begun operating. It took a while to commission the spacecraft. When it first looked around on the first day, it saw this scene, which shows what I think is a pretty typical scene of the surface based on the rovers and landers and orbiters that we've sent. It shows rocks, some of them buried, some of them perched on top of the surface, broken up loose debris, dirt, if you will, sand and dust. And you can ask, what is it that's exciting about this? It looks like just a typical desert scene. And the real driver is that we're interested in the surrounding terrain. It landed in the middle of Jezreel Crater, seen here in a topography image that's been colored by the altitude. Jezreel Crater is the site of an ancient lake bed. And the fact that there are standing bodies of water is what makes this an exciting place. The landing ellipse is shown there in the left, and that box in red shows you this image. What is exciting is that you can see the channel through which water entered, and you can see, just a moment, I'm going to turn on my laser pointer here. You can see here the channel through which water entered, and you can see where the water flowed into a lake, it deposited this delta. This is just absolutely typical of what a delta looks like on Earth when water flows into from a river into a standing body of water and deposits its sediment load. The fact that there was water here, that there was a standing body of water, is what makes this exciting. And the reason is that the overarching question for Mars really comes down to, did it ever have life there? What we see is that Mars appears to meet today, or to have met at some time in the past, all of the environmental requirements we would place on a planet for having life or for supporting an origin of life. It has access to all of the elements out of which you would build life, things like carbon, hydrogen, oxygen, nitrogen. These are present in the atmosphere and on the surface in minerals. It has a source of energy to drive metabolism. That source of energy can be sunlight, but it can also be chemical energy given off by reactions between water and rock. And as you'll see, it has liquid water, or had liquid water in the past, that allows life to exist. Mars meets all these requirements, and therefore it's not a stupid question to ask, could there be life? If there was, what was it like? And what we see is that Mars has liquid water. We see evidence for that in channels that look like runoff valleys Valleys formed by runoff of precipitation. On younger surfaces, we see these large flood channels where all of these had water flowing through it at one time or another. And note that scale bar in the upper left, 100 kilometers. This whole thing was likely filled with water. This is like the Mississippi in flood stage, but this was several billion years ago. We also see minerals on the surface that require liquid water in order to form. This is a global map of Mars showing where these minerals have been identified. All the evidence points to water having been abundant at different times in different ways. And it really opens up the possibility for life to have existed. We're not going to find this out from the Perseverance rover. However, Perseverance is going to collect samples that we're then going to bring back to Earth to study. The rover is collecting them. It will leave them to be picked up by a subsequent rover that'll be launched in a few years. And that rover will have a rocket, a MAV, a Mars Ascent Vehicle that will take them to orbit. They'll be collected by an orbiter and then brought back to Earth. On Earth, we can really study these in detail and get a real sense of whether there could have been life on the planet. I mentioned Perseverance rover. It also carries with it the Ingenuity helicopter. And if you've been watching the news today, you'll know that just this morning, the rover took its first flight and it sent back this image, which I think, again, is a spectacular image. This is from a height of about 3 or 4 meters, looking down, and what you see is the shadow of the helicopter on the ground. And I guess since Ingenuity saw its shadow, that means we have another 6 weeks of winter. Winter on Mars is a lot colder than winter on Earth, so I'm hoping that the spacecraft can survive through it effectively. Now, we're not just sending the Perseverance rover and the helicopter to Mars. It's only one of many spacecraft that have gone. I'm also a participant in the Hope Emirates Mars mission, which was launched by the United Arab Emirates, and it went into orbit just before Perseverance got there. It's a small orbiting spacecraft designed with just a few instruments to look at the atmosphere, and it's going to look at the atmosphere from the very bottom of the atmosphere, where what you think of as weather happens, to the middle atmosphere and the upper atmosphere, where the gases can escape to space. It's looking at the coupling between all the different parts of the atmosphere, and it's really the first spacecraft to be able to look at the whole atmosphere. In addition, it's the first spacecraft sent by the Arab world and was sent to arrive this year on the 50th anniversary of the founding of the country. Of course, I have to show the first image sent back once it got into orbit. You can see the 3 large volcanoes here, Olympus Mons, which is the largest volcano in the solar system, over there. The spacecraft and all the instruments are operating nominally, which is one of the most exciting words I can think of. Also, the other spacecraft to have gone into orbit is the Tianwen mission sent by China. And this, again, is one of the more exciting pictures I've seen. They had the idea to include on the spacecraft a CubeSat, a small thing about the size of maybe a loaf of bread. It ejected the CubeSat after it was en route to Mars, and that CubeSat was able to take a picture of the spacecraft. So we're seeing here their Mars spacecraft en route to Mars. The big container at the top has a rover. That rover will land in a month or two and hopefully will survive landing and be able to examine details on the surface. All of these spacecraft in different ways are trying to understand the history of water on Mars. And that history of water is one that you can see here reflected in the polar cap. This is one of the first images taken by the Chinese mission, but it's also something that we're continuing to explore. Britter mentioned that I'm the principal investigator on the MAVEN mission. MAVEN has been operating in orbit for about 6.5 years, and we're trying to learn about the history of water. We're measuring the loss out the top of the atmosphere to space of carbon, oxygen, and hydrogen And these are the main constituents of water and of CO2 that really dominate the climate. We're continuing to make measurements, and hopefully we'll go through an entire solar cycle. We're on track. Again, everything continues to operate nominally on the spacecraft. With that theme of follow the water that NASA's been following, NASA's planning to launch in the mid-2020s an ice mapper mission that we call MIM, Mars Ice Mapper. Very clever name there. It's going to map near surface water ice, both to understand the history of water ice and to be used possibly as a resource by upcoming human missions to Mars. In addition to these follow the water, there's also a follow the organics and follow the life theme. The European Space Agency is going to send a rover to Mars. It launches next year. Wait a minute, that's not it. Wait, this is the rover. This is the Rosalind Franklin rover, and it's going to drill down 2 meters beneath the surface to look for material that has been protected from destruction by galactic cosmic rays. And they're going to look for organic molecules that might be evidence of ancient life or might tell us about the possible production prior to life of organic molecules. Finally, I want to mention the potential for human missions to Mars. NASA has as its long-term goal the idea of sending people to Mars. This could happen in the 2030s, and there are people who are seriously planning for it. This particular picture is one version of what a mission might look like. It's Lockheed Martin's so-called Mars Base Camp, where they'll send the Orion capsule and support modules with people in it to orbit Mars and then be able to send from there something down to the surface. The idea of sending people to Mars really represents a major milestone in our exploration of the solar system. And I hope some of you will recognize this scene from the movie The Martian, which talked about some of the earliest Mars missions with people, hopefully sometime in the near future. And one of the exciting things, he's sitting here looking off at his base in the distance, which you can just see over here, and he's looking at the surrounding Martian terrain. Sending people to Mars is all about doing the science and understanding the history of the planet, the potential for life, whether there's life there. But it's also about exploring the idea of trying to understand what's in the world around us and how it relates to us. We're interested in understanding Mars as a planet because we live here on a planet, and we're interested in understanding the potential for life there and whether there's actually any life there, because we're life forms on a planet. We interact with our planetary environment, and we want to see the way that other possible life might interact with their planetary environment, and also understand whether we as life are alone around here in our corner of the galaxy, in our corner of the universe, or whether life might be widespread, especially now with the discovery of now thousands of planets orbiting other stars. It really raises the question of how widespread life might be. This all comes back to life on Earth and trying to understand the environment in which we sit. Exploration of Mars is an exciting topic, whether we're talking about exploring for its own sake, searching for life, or just trying to understand the evolution of a planet. So I'm excited about this, and I will stop there. And Britta, either turn it back to you or open it up for questions.
Thanks, Bruce. Super interesting. So my apologies, I forgot to mention this before Bruce started his talk. If you have any questions, you can put them in the Q&A, which should be at the bottom of your Zoom screen, and we will be happy to ask them of Bruce. While we're waiting for people to type their questions in, are there any questions from any of the other panelists? Anybody want to just unmute yourselves and ask a question? Okay, doesn't sound like it. All right, Dean?
Yeah, I can, yeah, sure.
Go ahead.
So Bruce, I was wondering if you could speak a little bit more on the specific aspects of Mars exploration that you are working on?
Sure. Well, I've been doing Mars exploration since I was an undergraduate working on the Viking mission in the 1970s. And my particular interest is this evolution of the volatiles, trying to understand the connections between the deep interior, the surface, the atmosphere, lost to space, what the climate has been like through time, and how it's evolved. We're using the MAVEN mission to look at the structure of the upper atmosphere. The upper atmosphere is the part of the atmosphere through which the gas from the lower atmosphere has to travel in order to be stripped away by the sun and the solar wind. And the evidence we're finding is that this stripping by the sun, by the solar wind, has been one of the dominant processes in evolution of the atmosphere. The images I showed show a planet with abundant water early in history, but the planet is a cold, dry desert planet today. And we think that it's this loss to space that caused that change. So while early Mars might have had life on the surface, we don't see much liquid water at the surface today, but there could be water under the surface. And that's going to be the next realm for exploring for life, looking in the subsurface and possibly the deep subsurface.
Cool, thanks.
Thanks. Okay, so we have another question. How do we ensure that the rovers or I guess it mostly applies to the rovers, but that the spacecraft that we send to Mars are free of organic material from Earth that might contaminate?
That's an important question. It's what we call planetary protection. And I'll tell you, we had to pay a lot of attention to it on our orbiter as well, in case we crashed onto the surface and could deliver organics or life. We go to great lengths, us and the rovers and the stationary landers, to clean the spacecraft and make sure they have the minimum amount of contamination by organic molecules or by living organisms. We do assays to test and find out how many living organisms are there. And the parts of the spacecraft that are going to come into contact with the surface for sampling it, for example, or analyzing it, are actually sterilized in order to make sure that if we discover life, we're not discovering terrestrial life that we've taken with us.
Okay, thanks. I have another question, which is whether evidence of water might have been destroyed by erosion or meteors.
Well, we see features on the surface that we think date back to earlier than 4 billion years ago. So we're able to get a lot of information about the history of the planet, and it's the surface geomorphology and the surface geochemistry that tell us that water was there. So I think the evidence for there having been liquid water is pretty compelling. And that's really been driving the program. The motto, the mantra of the Mars program has been follow the water over the last couple of decades. We're shifting now to follow the organics, search for life. And that's becoming the central theme. I like to think that it's not follow the money.
Okay, thanks. And then we have a question about the atmosphere. So was the Mars atmosphere thicker like Earth's atmosphere earlier in geologic time? And how does its thin atmosphere today affect the function of the Ingenuity copter?
The atmosphere would have to have been thicker early in history. And the reason is we see all this evidence for water, yet Mars early in its history would have been even colder than it is today. The sun was dimmer early in its history, and the sun has been heating up, Mars has been heating up. In order to have liquid water be stable, you would have to have had a thicker atmosphere that would produce greenhouse warming. Now, that could have been a lot of extra CO2, and that seems to be the most likely greenhouse gas. But things like hydrogen or carbon monoxide, methane, ammonia would also have contributed to the greenhouse warming. So the atmosphere today is a little bit less than 0.5% as thick as the Earth's atmosphere. And if you imagine trying to fly a helicopter in that, they put 2 rotors on it to get twice the lift, and they have to spin really fast. I think the number is 3,600 revolutions per minute. So that's 60 per second. That is really fast. And even with that, the payload, the mass of the rover can only be a couple of kilograms in order to be able to lift off the surface. So it has a solar panel to charge up, a battery, a camera. Cameras are very light these days, and not much else.
I know we have some plane and helicopter enthusiasts who I'm sure were very interested in the answer to that question. Following up on the question about the thin atmosphere, so what would happen if there was water on Mars right now? Like if Matt Damon went and dumped a glass of water on the surface of Mars, would it evaporate? What would happen to it?
Well, Matt Damon would evaporate if he wasn't in a spacesuit. If you took a bucket of water and threw it onto the surface, the temperature of the surface averages about 50 degrees C below the freezing point of water. So the water would probably freeze or evaporate into the atmosphere very quickly. Now that's the average temperature. If you go to the equator at noon, it probably warms up to room temperature. And room temperature for me might be a little bit different. You can see it's actually snowing here outside. But temperatures get up to room temperature, but the atmosphere is so thin that liquid water would not be stable. It would evaporate even when temperatures were above the 273 Kelvin melting point of ice.
Okay, can you talk a little bit about what type of life we might be looking for that might be able to exist in such a seemingly harsh environment?
Well, first of all, this whole discussion, when I've said life, I'm referring to microbial life. I can't imagine that evolution could have gone far enough to produce bunny rabbits or kangaroos or anything like that. Microbes can exist in what we think of as extremely harsh environments. We've seen that just in the past few decades here on Earth, where microbes exist inside of ice, inside of rocks. If you go to Yellowstone and look at the temperatures in the hot springs, that's water at and above the boiling temperature of water, and microbes exist quite happily there. So Mars really probably doesn't have too harsh an environment. If you have liquid water, then that opens the possibility for life. You can have liquid water today under extremely, I'll say, unique circumstances. It's too dry for Earth life to exist in that liquid, but maybe not any life. It's possible that Martian life could be there. And early in history, with liquid water at the surface, that would not have been too harsh an environment. And today, you could have water existing quite happily under the surface, maybe a kilometer down, and life could exist there. We've seen life kilometers below the surface here on Earth, living in water that sits in the pore space inside of rocks. And that's quite a pleasant environment for them. And almost identical environments would have existed on Mars. So again, with all the different environments, I don't think it's a stupid idea to imagine that life could be there. And we're going to find out if it is there.
Okay, another question about, by the way, we have, Bruce, your talk was pretty quick, so we have a lot of time for questions, which is probably the way people would prefer it, actually. We have a question about the relationship between the volcanoes on Mars and its climate and its atmosphere.
So the volcanoes, first, there are abundant volcanoes. I didn't dwell on them because I wanted to talk about the surface missions, but we see large, what are called constructs, big mountains that are volcanic. The Tharsis volcanoes, Olympus Mons, are very similar to the Hawaiian volcanoes. And in fact, the entire surface is thought to be volcanic, produced by flood volcanoes or early melting of the planet. The fact that we see volcanoes is telling us about the deep interior of the planet and the geophysical history. But the relevance here is that volcanoes give off gases, and it's through those gases that the early atmosphere would have formed. In fact, we think that volcanoes are still probably active on Mars, and that gases are being put into the atmosphere even today. So I think of volcanoes as a source for the atmosphere, and then the sun and the solar wind stripping that atmosphere away to space. Early on, the source was bigger than the sink, and we built up a thick atmosphere. Then the sink was bigger, and today neither one is terribly significant, but probably both are ongoing. We're losing atmosphere at a rate of a few kilograms per second, and we're supplying atmosphere from volcanism. Volcanism probably is something like the equivalent of a cubic kilometer of rock per year. That sounds like a lot, but it would get totally lost over the whole planet. But we think that volcanoes are still active today.
Okay, and then we'll do one last question for you before we move on to the next talk. What does the history of the atmosphere and the environment on Mars say about the potential future of our environment and our atmosphere on Earth?
The same processes that operate at Mars operate at Earth. And that means that we are losing gas today, and we did lose it in the past. But the Earth has a magnetic field that creates a magnetosphere, and it causes the solar wind to stand off at a great distance from the planet. So the solar wind does not effectively strip gas out of the atmosphere today. But we can study the same processes in the vicinity of the Earth, on the ground, looking at volcanoes and the outgassing to the atmosphere. In space, looking at the way that gas is lost and the way the solar wind interacts with the upper atmosphere. All of the planets have similar processes. And in fact, one of the cool things to me is the fact that nature has given us a wonderful experiment. With Earth, Venus, and Mars, we have planets that have different thicknesses of atmosphere, have had different histories. Two of the planets have no magnetic field. One has a magnetic field. They're all at different distances from the sun. And it lets us try to really understand how all these processes work. And that's going to be important for extrapolating to what's going on around these planets that we've discovered around other stars. We want to understand what their climates are like. Pretty soon, we're going to be able to detect and measure the thickness of their atmosphere. And then by looking at the planets in our solar system, we'll be able to understand what processes have operated and which may have life.
Very interesting. Well, thanks, Bruce, very much for a wonderful talk. And just to let everybody know, there's one or two questions we didn't get to answer, but we're going to move on to the next talk. And Bruce is going to stick around, and we might have time for more questions after the next talk. So our next speaker is Cynthia Gunderson. Yes, I am related to her. She has a mechanical engineering degree from the University of Maryland and a master's in mechanical engineering with an emphasis in space systems from George Washington University. She worked at NASA for 11 years prior to moving to Miami and founding AMU Engineering. While at NASA, she worked on mass spectrometers for several missions, including Cassini. As an owner of AMU Engineering, she has provided extensive design and development support to NASA Goddard Space Flight Center, working on mass spectrometer designs for 5 spaceflight missions, including Curiosity and Maven. She's currently supporting the design and development of the Dragonfly ion trap mass spectrometer, which is heading to Titan in 2027. Very long timelines on those projects, I know. All right, without further ado, Cindy, the screen is yours.
All right. Can you see it, Britta?
Not yet.
Let's see here. Okay, 1 second. Here.
There we go. Perfect.
There we go. All right. Well, thank you, Britta, for that introduction. And Bruce, as expected, you're a tough act to follow. So hi, everyone. I want to start by giving a little bit of history about AMU engineering. To begin, most of our collaborations are with the Planetary Environments Lab at NASA Goddard Space Flight Center in Maryland, which is primarily known for successful spaceflight mass spectrometers. I did start working with that lab 30 years ago, fresh out of college, when it was called the Atmosphere Experiment Lab. And I was hired to work on a mission called Cassini, as Britta pointed out, which had a mass spectrometer on an orbiter, which headed to Saturn, with another one on its probe that was sent to Titan, which is a moon of Saturn. I was a NASA employee back then, but fast forward 11 years later, after marrying the love of my life and choosing him over a civil servant job, I ended up in Miami, Florida. But fortunate for me that NASA group asked for my help developing instrument configurations for proposals. And that's when I decided to start AMU Engineering with my husband as vice president. I do have to say I'm so fortunate to continue to work with them today. So it's been 20 years in this capacity. I showed Curiosity on the title slide as it's the first Mars mission that I worked, as well as the first spaceflight mission for AMU Engineering. So on this slide, I'm showing the only 2 Mars missions that I have worked from proposal to launch. The Mars Science Laboratory, MSL, referred to as Curiosity by most, was launched in November 2011 and landed in August 2012. It was 2003 when I first started working on an instrument proposal configuration for this mission with a scientist at Goddard named Dr. Paul Mahaffey. We found that we won in 2004, which was tremendous news, as we had a 1 in 50 chance of being selected. And I remember thinking, well, it was impossible, but it wasn't. The instrument that we proposed is called SAM, and it sits in the belly of the Curiosity rover. SAM stands for Sample Analysis of Mars, and is a suite of instruments, as you can see in that photo, including a mass spectrometer. The 2 inlets that are pointed out right here on the rover, they basically accept the solid, the dust and the rock that's picked up by rovers, the rover's arm, and is deposited into those right there. So it's not the only instrument on the rover, which is important to remember, because I'm going to pretty much only talk about SAM. There are also many cameras. Not as many colored ones that are on Perseverance, but there are a couple of colored ones, and the rest are black and white. There's also environmental sensors and other chemical analyzers. MAVEN, in the image on the right, launched in November 2013. The mass spectrometer on this mission was heavily based on heritage from Cassini and SAM, and is called NGIMS, which stands for Neutral Gas Ion Mass Spectrometer. It's attached to a payload platform that hangs off of the spacecraft. And this is indeed the mission that was led by Bruce Jakowski, our previous speaker. All right. So this is going to be a video, and I really hope it comes through for everybody. What I want to do with this video is to give a brief overview of a mass spectrometer, and a big thanks to one of my colleagues who provided this for us. So let's start it, and it shows a mass spectrometer similar to what is in SAM. It's called a quadruple mass spectrometer. This is because of the 4 long rods that make up the center of the instrument, as you can see here. This part of the mass spectrometer is called an ion source. There we go. Oh, come on. Whoa, oh no. Now imagine you have a sample that's been turned into a gas, and you want to find out if it contains certain things. The gas is sent into the mass spectrometer, first hitting the ion source. Here a stream of electrons hits the molecules, breaking into fragments and giving each fragment a charge. There we go. Okay, so next the fragments enter what's called the analyzer. Here they're separated based on their mass. Then the analyzer is tuned so that only the fragments we want to see make it through. Everything else flies off in a different direction. After this, the fragments hit another subsystem called a detector, and scientists record the data. If you're looking for more than one kind, the analyzer can scan across a range of fragments, building up a record of not only what kind, but how many. Once you have these results, called a mass spectrum, you can verify that your sample in fact contains what you're looking for. The bottom line is that the mass spec has proven to be a very valuable tool for studying molecules for planet exploration. And this is indeed the SAM mass spectrometer that I've spent a lot of time on during that development. So why can't we just fly commercial mass specs? I really want to focus on this tonight because there are challenges associated with designing these mass spectrometers or any spaceflight mission. To begin, minimizing volume and mass is extremely important. And I have never worked on a mission where this wasn't important. And I'm going to elaborate on that in the next slide. A second reason is that our instruments are going to very extreme environments. Space is cold. Other planets have their own challenging environments, very different from Earth. And next, achieving reliability is an absolute must. Over 95% of mechanical parts are custom. We're always working on a tight schedule and have little schedule for failures during the instrument development. All instruments and subsystems get heavily tested before going to the launch pad. And we are all painfully aware that if a mass spec fails in space, you can't bring it back to the shop and repair it. So focusing on mass and volume, I show a single quadruple mass spectrometer on the left. And this is a spaceflight. So I show two single pole or single quadruple mass spectrometers. I show a spaceflight version and a commercial version. Now, if you look at the table on the right, you can see that the mass and volume of the spaceflight version is about 20% of a commercial unit. But why is mass and volume so critical? And the bottom line is, let's see if this comes up. Whoops. Oh, I can't quite see my whole screen here. But if you see the rocket on the left, the payload mass in a rocket accounts for about 2% of the total rocket mass. So the larger the payload, the larger the fuel requirement to launch it into space, the bigger the rocket, the more expensive the mission. And yes, it does come down to cost with these missions. Remember, your taxpayer money is paying for it. As for power, it's certainly not a driver for a commercial mass spec, as you can just plug it into a wall socket, right? Well, we can't do this in space. So we have to rely on other energy sources. Maven relies on solar panels. It's a nice orbiter, doesn't have a lot of dust around it. But Curiosity and Perseverance use a radioisotope thermoelectric generator, otherwise known as an RTG. The RTG generates power using a temperature difference caused by radioactive material. It doesn't depend upon the sun to charge a panel, allowing instruments like SAM to take measurements through the year and at night on Mars. Also, Martian dust has caused a problem in the past Mars lander missions, coating solar panels and drastically reducing the performance over a period of time. There are many benefits to moving to the RTG energy source for Curiosity and Perseverance, and it will also be used to power Dragonfly, a multi-rotor vehicle being sent to Saturn's moon Titan. What kind of environmental considerations do the instruments have to consider? Well, it depends on where they go. Curiosity landed in the Jezreel Crater, which is fairly close to the Mars equator. The lowest temperature that Curiosity has experienced has been around -70°C, and the warmest has been around 0°C. And this was detected by a temperature sensor on Curiosity. Prior to that, they were going off Viking data, and that forced the design of these inlets to -150°C. The only thing on SAM that's exposed to those temperatures, and again, it's not that 0°C, that's a pretty easy temperature to deal with, it's a -70°C. But the only things of SAMs that's exposed to that are the two solid sample inlets at the top and two gas inlets on the side. The rest of SAM is buried in the belly of the rover, where the lowest temperature it sees is -40°C, and the warmest temperature is +50°C. This is a fully tolerable range for the SAM electronics and a couple of elastomer seals that we have sealing the mass spectrometer shut. The carbon dioxide environment, coupled with the low atmospheric pressure, so it's like 1/100th of Earth's atmospheric pressure, introduces challenges for the high voltage electronics. So special potting has to be used on the in the HV connectors to prevent electrical arcing. Particle radiation from solar, wind, and cosmic rays can be detrimental to electronics, 13 times that of Earth, which is why these missions fly radiation-hardened electronics. This makes the electronics much less susceptible to damage or malfunction caused by the radiation. So another environmental specification that we receive from a spacecraft team at the start of a mission is vibration test levels. These levels given to us encompass all vibration events that we see during a mission. The spec always takes into account the rocket launch loads, which can vary greatly depending on which rocket you're launching on, and may have to include vibrations of landing events. Not every instrument we fly up is going to have to go through a landing event, but instruments on landers like, or spacecraft like Curiosity, landers like Curiosity do. So we design, analyze, and test the specifications, assuring the instruments do not fall apart. In the pictures I want to show two vibe tests because we vibe the mass spectrometer 2 times. We vibe it the first time without its electronics or its structure that mounts it to the spacecraft. And we do this because there are 50 bare wires in that instrument housing, which is titanium. And those wires are spot welded to small electrostatic lenses. If the workmanship test truly is a test to verify that those wires are not going to fall apart due to workmanship, or it's not going, that ball is not going to break due to workmanship. It's a much lower test than what the instrument's going to go through next. So then after you integrate it to its structure and its electronics, you attach it to a giant fixture, which mimics the spacecraft mounting, or gives it a spacecraft mounting interface, and you vibe it to the actual highest required vibration levels. Other environmental testing that's very critical for all instrumentation is thermal testing. So 3D modeling, mechanical and thermal analysis, with the 3D modeling, I should say, and the mechanical and thermal analysis, they play big roles in the instrument development. The testing, whether it's vibration testing as on the last slide or thermal testing shown on this slide, provides the information required to verify the analysis models. This verification reduces risk of failure, super important as you're marching through these tough timelines, and increases confidence in the design. Often the mission thermal environment can produce the highest stresses on our components. Using a combination of different materials required for certain instrument function have to be carefully looked at from the thermal expansion perspective across the instrument survival temperature range. The picture shown here of this mass spectrometer, this is the same mass spectrometer in the previous slide, but it's shown in a thermal test chamber at Goddard. And now I want to take a few minutes to talk about SAM, because SAM was the most challenging development ever. It was just an incredibly large instrument suite. My primary job on SAM was to design and help develop the mass spectrometer, which you saw in the video, as well as the gas processing system that ties all of the major components together. The major components of SAM included the Goddard mass spectrometer, a gas chromatograph from our French colleagues, which is called GC in the picture, which is the GC in the picture, a tunable laser spectrometer from the Jet Propulsion Laboratory, the TLS in the lower left-hand corner of that assembly picture, and a 72-cup sample manipulation system, which is a fancy carousel, which you see in the middle picture, for receiving and delivering samples to the gas processing system. It was designed and built by Honeybee Robotics in your own New York City. So there were many design challenges, and one that stands out was fitting all of the required instrumentation into the allocated volume provided to us from the mission folks. You get a good sense of size in the picture on the left. I once heard of, oh, well, that's another story. Thermal challenges included having to heat some of the sample analysis subsystems up to temperatures between 612 degrees, 600, I'm sorry, and 1,000 degrees C. For comparison, your stove surface at its highest temperature is 200 degrees Celsius. These subsystems took years of development and testing, and eventually utilized custom heaters, because you can't really find heaters to do what we needed these heaters to do. And these heaters, and anytime you're designing a custom heater like that, that's being built by our very talented technicians at Goddard. Another personal challenge for me was the extensive gas processing system. It has 51 individual 1/8-inch gas lines. Well, I should say most of them are. There's a few capillary lines in there. 52 microvalves on 19 custom manifolds. And these manifolds have channels carved into them to direct the gas to the different components. The manifolds and plumbing lines are required to be heated to 135 C while keeping that gas path vacuum leak tight. It was so critical for every sealing surface of that contamination-free gas path to be highly polished and inspected under magnification to find and fix any defects before you even begin to put it together. And then accessibility in this tight instrument volume was critical to be able to tighten those little 1/8-inch plumbing fittings of a pipe if it should spring a leak during testing. And these are just a few of the development challenges that I had to address during my time on SAM. So I wanted to throw up a typical instrument development schedule. It all starts with instrument requirements and any new technology type of subsystems that you have on as part of the instrument development. So you need to address those as well right away if they're what they call low technical readiness, as you need to bring them up to a tested design as soon as possible. Now I want to just say something about this development. This is not reflective of SAM, because SAM was anything but typical. And I have to agree with Bruce, it's probably not reflective of Maven, because Maven was a very fast-paced instrument development, which was phenomenal. But I'd say this is reflective of the majority of the space flight, the mass spectrometer builds, or was, I should say, we're going much faster these days in the past. So after we address any new technology developments that we have to, where we have to buy down any kind of possible risks, we move into our heavy design and analysis phase. And this is of the entire system, from the nitty-gritty guts of the mass spec to the supporting electronics and structure, baselining heritage as much as we can, as that probably helped us win the project to begin with. That's always something we have to keep in mind. Don't go away from heritage if it works. During this part of development, all the design and analysis is critically reviewed by very tough NASA review panels, and then we start having parts fabricated. Every part that gets fabricated requires a release drawing with any critical subsystem lead engineer and QA weighing in. So we're just not making the decisions for ourselves as the mechanical engineers. We have to have sign-offs from thermal engineers, electrical engineers, scientists, you name it. Nothing goes unchecked. It's super important to use vetted and high-quality machine shops, as there is rarely scheduled to absorb bad parts. Once parts are in, they are kitted for each subassembly for the highly skilled assembler to work their magic. And I can't tell you enough how critical it is to have the right tech team working on these instruments and technicians that stay to work on the next instrument. Mass spectrometers are some of the toughest spaceflight instruments just from the sheer number of parts required for it to work. Continuing with the schedule, the instrument is workmanship vibed. Let's put up our technicians. Is workmanship vibed, calibrated, and integrated, and then integrated with electronics and structure. It goes through all required environmental testing, hopefully passing with flying colors. After final functional testing to assure the instrument is still working, it gets delivered to the spacecraft. It will go through spacecraft system testing and eventually make it to the rocket and launch pad. So we're generally looking at let's say 3-year development time. And I don't think I have, there we go. Typical, well, I can't see it though, but typically it's a 3 to 4 year instrument development time. Then we deliver it to the spacecraft and they deliver it to the rocket, and that's usually another year to year and a half. And then we go on to launch. So I have to say there's no bigger reward than working on these missions. And this is a picture of my family and I at L-4 minutes till takeoff. This is at Kennedy Space Flight Center for the launch of Curiosity. I can say that after years of working this mission, I did have tears in my eyes watching that rocket go up. I'm so happy that we were able to complete a successful build and delivery of SAM. However, the biggest reward for all these missions is when it reaches its destination and starts sending us back the science data. That's a pretty amazing feeling to have. And then I wanted to, as my last slide, I wanted to put this slide in to show a team of engineers, some of whom are subcontractors and that have worked with me since SAM days. And that's Krista Budenoff and Akif Ursahen. And then the rest are more recently hired AMU engineering employees, with the majority from the University of Miami engineering program. For the last 4 years, they have been and will continue helping with the current missions and new technology work. Well, the biggest project, as Britta pointed out, that we are currently working on is the design and development of a mass spectrometer and gas processing system, very similar to SAM from that perspective. For that Dragonfly mission, which is set to head to Titan in 2027. Talk about environmental challenges. I wanted to give all of the members of this team kudos, as this work is anything but trivial, and I couldn't ask for a better team to move forward with. And that's how I'm going to end it. Thanks so much for listening, everybody.
Thanks so much for your talk, Cindy. And I just wanted to say it looks like a number of your members of your team are logged on to this. So I'm sure they enjoyed the shout out.
That's nice.
So we have a bunch of questions for you. I hope you're ready.
Right.
So the first sort of existential question is why you would want a mass spec in space to begin with.
Why? Because we would like to know what those atmospheres is made of. We would like to know what the soil. We would like to know what the ground, the rocks have inside of them. What are the constituents of all of these different bodies out there in the solar system? We have some idea from prior missions, but the mass spectrometers, the sensitivity are getting better and better. And again, SAM has done just remarkable work up there on Mars. It has a drill that drills into the rocks, delivers the rock samples to SAM. It also has its direct inlets tubes that's bringing in the atmosphere of Mars. It's basically telling us exactly how much, what is in that atmosphere, what is in that soil, what is in that rock, and how much of each constituent's in there.
Great. And then we have a number of questions that are all kind of on the theme of, you mentioned that you have to sort of, on some level, have expectations for what kinds of molecules you're expecting and to sort of calibrate the instrument. So we have a bunch of questions about how you do that and how you deal with the potential for detecting molecules you might not be expecting, and how you calibrate the instrument to work properly on Mars when you're, what you're used to is what's on Earth, and you might not know exactly what the conditions are going to be.
So I do think that I'm not a scientist, I'm an engineer, but the scientists have quite a bit of, and Bruce could help with this, data from past missions to go on. And so we were hoping to find organics on Mars, and we did find organics, but for that reason, we flew a mass spectrometer or a group of instruments that could detect a very large mass range. And so what you're doing is you're trying to fly an instrument that can detect a large enough mass range to detect anything that could possibly be there based on all that prior data. That's the best answer I can give.
Okay. And we have, just following up on, you mentioned organics. We had another question about that. So were the mass specs also able to detect non-organic compounds? And, maybe that wasn't the focus, but was that also a capability?
Sure, it's capable of, yes, of course. It's capable of detecting non-organic and organic compounds.
Okay, great. Next question is, what kind of scenarios did you model for instrument failure after launch? And did any of them occur on any of the missions that you worked on?
Instrument failure after launch, we never designed. Oh, no, usually if there are if you can envision a failure to happen, hopefully you have the money to address those risks. And for example, fly redundant systems. And we did do that on SAM. We ended up flying 2 wide range pumps, which are these pumps for basically evacuating the instrument after a sample and helping to pull sample through at the same time through the mass spectrometer. If one of those had failed, you'd be in big trouble. And so, so not too long into the mission, I remember us having to make room for that extra pump just in case that happens. So as we're developing these missions, the scientists really start weighing what are the most likely risks to occur, maybe based on new technology developments that we are putting onto these missions. This was the first time we had flown this wide range pump on an instrument. We're flying it on the MoMA, on the ExoMars mass spectrometer that Bruce talked to as well. But that was an example of where they foresaw a possible problem and they addressed the risk.
Okay, thanks. I just want to ask my team if there's any other questions specifically for Cindy. And if not, I think we have a couple of broader discussion points. So I think we'll bring back Bruce.
Wait, can I ask a question?
Oh yeah, go ahead, Dean.
So you said that there are organic molecules found on Mars. What were those?
Well, I know, I mean, so I know that they have seen, one thing I know that they've seen, and are methane spikes. I mean, and that's something that they don't quite know why or where it's coming from, but that's an example of an organic that they have seen signs of on Mars, that with varying intensity over the seasons. And then maybe Bruce can talk to any other organics that he think are important to mention.
Cindy, first, that was a great talk. Thank you.
Well, thank you.
I don't remember the names of the organics, unfortunately, but what I do know is that they could be decay products of life. They could have been brought in by meteorites, or they could have been produced in situ by geochemical processes for the specific organics that they detected. I think the goal from here on would be to look for other molecules, other organic molecules that might help distinguish between those different options.
Very good. Okay, we have one other question for Cindy, which is, we've been talking a lot about Mars, but we know that you're working on this mission to go to Titan. What are some additional challenges that might be different from those on Mars, or more challenging than the ones with the Mars missions?
So the two biggest challenges of Titan are the time it takes to get there. It's a 9-year cruise, so you have to make sure that you can survive that 9-year cruise. That's a long time to just be cruising through space. And so that's one thing. And then it's cold. It's really cold. It's 98 Kelvin. That's super cold. So here we are trying to operate an instrument that really doesn't want to be any colder than minus 40 C in a 98 Kelvin environment. And so therefore you have to have, but you want to ingest cold, you want to ingest sample that is close to the environmental, to the actual temperature of the environment. So you don't want that to warm up too much. So then you have this barrier between the warm and the cold section that you have to deal with. That's super challenging. We're going to be flying on a drone, and that's going to be super fun. And so we take up basically if you can imagine a pickup truck, we're in the cab of the drone, and right now it's super mass critical, so we have to keep mass down. The mass spectrometer is not a quadruple mass spectrometer. It's a different type mass spectrometer called an ion trap mass spectrometer. And it's mounted, for the first time, instead of mounting to a base, it's mounted to a wall, which is your wall that's separating your cold zone from your warm zone. So there's just a lot of mechanical challenges. There's a lot of science challenges. There's tremendous amount of thermal challenges that we're dealing with. But we're very excited to work it. And we just started. So we haven't hit our preliminary design reviews yet. We're pretty early into it, but it's good. It's going to be probably close to as challenging as Sam was.
And you have the psychological challenge of waiting those 9 years for it to get there and see if it works, right?
Right. Yes, we waited 7 years. I waited 7 years for Cassini. So I've been there before, which also we put a probe on Titan, so that was 7 years, but this one will be 9. Yep, you're right.
Amazing. All right, so we have a couple of broader questions about Mars exploration that I wanted to ask both of you. So one, I think Bruce gave some estimate written in the Q&A, but we had some questions about sort of when you think there might be human beings on Mars, and maybe what some of the challenges that we still need to overcome before that can happen. Aside from the money, we'll forget about that challenge for now.
What's a one-way ticket? That's kind of tough to think about. I mean, there's tons of challenges associated with it. As far as when do I think? I mean, I think the goal is to have them on Mars by 2030. I don't know, Bruce, do you think that's possible?
I think that 2030 is pushing it. But the real answer to me is we're going to have people on Mars about 15 years after we make a real commitment to doing it. So if we decide today that we're going to go forward full speed, by the mid-2030s, we can do it. It takes that long to solve some of the problems that are sitting out there, develop the hardware, test it, and then really implement a mission. In terms of the challenges, I think the big things are, how do we get something to last that long that involves people? Because that's the starter. A round trip mission, minimum of 2 years, more likely 3. And they would have to survive, the hardware would have to survive, operate in space for that long without any chance of abandoning it if things go bad. You can't just decide to go home like you can in low Earth orbit. That's the biggest technical challenge. The others deal with Mars, things like, how do you survive the higher radiation environment? How do you deal with the dust on Mars, which can have oxidizing agents attached to it that would be potentially detrimental to our health? these sound easy, but they're not trivial problems.
If you guys were given the chance, would you go?
Hell no.
Me neither.
I'm loving this past year because I didn't have to get on an airplane once.
I'm sure your spouses are glad to hear that. Okay, and then the other question that we had was, let's say we find some life on Mars, what would that change for humanity? I mean, what would we do differently than we do now? How would it, how would that change things?
My funding would go up, but I don't think that's what you're asking. It's a philosophical issue of whether life on Earth is the only life that's out there. And if we go to Mars and we find life that isn't genetically related to terrestrial life, that's a really big deal to have discovered an independent origin of life. One is a unique circumstance. As soon as there's two, there can be many, and the universe can be just teeming with life. I think of it as analogous to the recognition by Copernicus that the Earth goes around the sun rather than the sun going around the Earth. You're hard pressed to think of how that makes a difference to your day-to-day activities, which one goes around which. I could think of some examples, but they're pretty arcane. But it makes a really big philosophical difference in how you view the world around you and what it means to be here where we are.
Yeah, I think that would be pretty mind-blowing for people, even though it's something that, we've been looking for a while and sort of contemplating, and even though it would probably be microbial still, I think that would be pretty mind-blowing for sure. All right, well, we want to thank both of you very, very much for taking time out of your day to share your work with us. I also want to thank our audience, and I want to thank the New York Taste of Science team, Catherine, Rosa, Dean, and Rosemary, who all helped make this event happen and helped it run pretty smoothly. We really hope you enjoyed this event. If you really enjoyed it, we lost our biggest source of income by not being able to have an in-person festival. So if you can spare anything for a donation, we'd be grateful. We are a nonprofit organization. You can go to tasteofscience.org and there's a donate button on our homepage. Just as a reminder, this event is just one in a series of events that we'll be holding throughout the next 2 weeks. Catherine, if it's not too much trouble, you could put the homepage up again. But we have a number of other events going on in the coming days. And you can find out all of those at our homepage, which is tasteofscience.org. They're being put on by different city chapters of Taste of Science across the country. And New York itself will be hosting one more event on April 29th about birds. If you plan to attend additional events, you can download a festival passport on our homepage, and you'll get digital stamps for each event you attend. And those with the most stamps at the end of the festival will get some Taste of Science swag in the mail, just like you will if you won the bingo game, if anybody won that. Again, more information on that is at our homepage, tasteofscience.org. This event will be posted, the recording will be posted to our YouTube channel, along with links to find both of our speakers so that you can find out more about them. We'll also send you a survey for your thoughts about this event. We'd love to hear any feedback you have. And there's information in the survey in case you're interested in volunteering for Taste of Science in any of the city chapters that we have across the US. This year has been obviously a limited experience volunteering with Taste of Science, but hopefully once the world gets back to normal, it's a really, really fun thing to do. Get to hang out with really interesting people and learn about what they do. So that's it from us, and we look forward to seeing you hopefully for in-person events in your home cities this fall. Thanks a lot, everybody. Good night.
Thank you. Good night.